Hey folks, Morgan back with you on page number 3 of the gases outline for AP Chem. And we're going to talk about Robert Boyle. And I've got to point out to you that he's Irish. Don't get to say that very often in a chemistry class. This gentleman is the inventor of the vacuum pump, the precursor of the modern vacuum cleaner, but for this purpose, for this lecture, a scientific instrument which can be used to change pressures. Now, it allowed our first experiments into the world of gases where we'd have variable pressures, and Boyle showed that pressure times volume were inversely proportional. And if you could return to the first page of the lecture outline and see that this meant that we would get a graph that looks something along these lines. Okay? Now, most textbooks incorrectly state that Boyle's law is P1 V1 equals P2 V2. That is an equation that is representative of the concept. That's not his law. Boyle's law states that pressure and volume are inversely proportional. That is, one goes up, the other goes down. Okay? This is an algebraic equation. Now, personally, I kind of prefer PI. VI equals PF VF. I like initial and final. Okay? The initial state of the gas, the final state of the gas. This is a two-state problem. We have a balloon under one set of conditions. We change it, different set of conditions. Okay? Now, there is an implication here that we didn't make a big deal about in the past, but I am going to this year. Temperature and moles are constant. That balloon has been tied off. So no gas can get in or out, moles are constant, and we're holding it always at the same temperature. Okay? Now, for a particulate level diagram, what does this behavior look like? Well, let's consider that we have a rigid container. Look the word up if you're having trouble with it, but basically we're meaning inflexible. Now, I'm saying that this one is a 2-liter volume. Now let's just picture 3 particles, which is implying 3 moles, but I only want to draw 3. They are in motion, which is why I'm drawing them as arrows. Okay? These arrows are going to be colliding with the walls of the container. Those collisions with the walls are what causes pressure. That's what pressure is. Collisions with the walls of the container. And the force exerted per unit of area is the pressure. It's quite random. Okay? The velocity is a constant velocity. And it's a constant velocity because we are at a constant temperature. We're talking about, an average velocity in here. Now, we're going to do a change here. We will keep temperature and moles constant, so nothing else is going on. And we will suddenly use some magic machine to make this box 1/2 the size it was. Okay? We take it from 2 liters down to 1 liter. Now, the point I've been trying to make here with the constant velocity is that these particles are still moving at the same speed. What's going to be different? They're going to be hitting the walls twice as often because they don't have as far to go to get to the walls. Okay? So if they're hitting the walls twice as often, that means the pressure is going to be doubling. Because pressure is the collision of the particles with the walls of the container. Force per unit of area. And the area is quite a bit smaller now. Okay? And the force isn't changed because they're still traveling at the same average velocity. Okay? And that's actually a pretty good description of what's going on right here. Cut the volume in half, the pressure's going to double. Okay? Now, I'm going to shut up for like 5 seconds, but you pause me and you're going to go and you're going to watch a video. It's next up on the list by one of the greatest chemistry teachers I've ever met, a man named Lee Merrick. He is a master demonstrator. He is so good that for almost 20 years, he made appearances quite regularly on The Late Show with David Letterman, although now different people are hosting it. It's Stephen Colbert at this point, I think. But Letterman used to actually take students from his classes and appear on The Late Show blowing stuff up. It was really done well. Started back when I was in college. I'm not going to deny it probably had a pretty big influence on my demonstration style. After I started teaching, I had the very good fortune to meet Lee, and we became pretty good friends in about the last 10 years. He's been in the classroom for over 40 years. He's retired now within just the last couple of years. And he has really given me some great tips about the art of the lecture demonstration in that time frame. And I typically see him once a year in all of our chemistry teacher meetings. Okay, so I'm gonna shut up, go watch Lee. Okay, now I assume you're never gonna look at a marshmallow peep the same way ever again, okay? But let's talk about the balloon to begin with. That's not a rigid container. That balloon is a flexible container, okay? And he actually had to cheat a little bit to get the balloon to pop. There was a little pin that was in the top of that bell jar to help it pop, okay? But imagine we have this 2-liter container. Actually, let's start over here. Let's reverse it. Let's start with the 1-liter balloon, okay? Now, inside, we've got particles flying around, and they're hitting the walls of the container, okay? And outside, same thing. Air inside, air outside, everything's balanced, and the balloon's just sitting there tied off. N and T are constant. He puts it in the bell jar and he takes the air out of the bell jar. In other words, these are going to disappear. Okay? So what's inside is pushing out, but there's nothing to balance it on the outside by pushing in. What happens? That balloon is going to get bigger. These forces are no longer balanced forces. Okay? Now, go watch the next video, which is probably a little more, well, let's say it's a little less theatrical and a little more scientific. Okay, so I think in that one you actually see more of what the science is, what the explanation is for what's going on. But Lee's just so good at it, I wanted you to watch that one first. Okay, that's page 3 of the outline.